Last class we were talking about waves, electromagnetic waves propagating in a conductor. And I just want to remind you of the two cases, the two primary cases that we talked about. There was a poor conductor. And by that we mean that the conductivity is less than, let's say much less than, epsilon omega divided by 4 pi. The reason for all the constants is because we want the imaginary part of the dielectric function to be much smaller than the real part of the dielectric function. And if that's so, then we can do a Taylor expansion to make the square root. And the effective complex wave vector is omega, approximately omega over c, square root of mu epsilon plus I 2 pi sigma is approximately that, right? So what that means, again, because this is still going to be bigger than that, is that we're going to have a wave whose wavelength is determined by omega c and square root of mu epsilon, but whose wavelength is short compared to the conductivity, or rather to the decaying term. So this is going to lead to decay. This is going to be the oscillating part, and so we'll see a wave that decays. Okay? For a really good conductor, then dielectric constant, the real part, is much, much less than 4 pi sigma over omega. Same term, I just rewrote it slightly, right? The conductivity is large, right? And then in that case, complex dielectric function is like this, omega over c times 1 plus I square root of 2 pi sigma mu over c squared. So basically, the real and imaginary parts have the same magnitude. Okay? And what that means is that we end up with a wave that basically decays. There might be a teeny weeny bit of overshoot, but it's almost underdamped. Probably it's critically damped. Okay? And if we look at the imaginary part of that, we can deduce an effective decay length, which is called the skin depth, delta is c over the square root of 2 mu. No? And because it depends upon frequency, right? Actually, first of all, I should tell you that overall the conductivity doesn't change a whole lot as a function of frequency over a fairly wide frequency range for many conductors. And so it turns out that the primary dependence of the skin depth is on the frequency, because there is a frequency that appears explicitly in there. And so the higher the frequency, the smaller the skin depth is. And for a typical metal, copper in the microwave regime, so that would be, I have a particular interest in this, 10 to the 9th hertz or so. The skin depth is of order 10 to the minus 4 centimeters, okay? Around a micron. So I think I finished up the last class by telling you that if you then try to send a microwave signal, power, down a wire, what happens is that all the field ends up sitting on the outer 1 micron of the wire, and all the current ends up flowing on the outside of the wire. So you don't need all that copper for a microwave signal. Basically, you send it in a coaxial cable, and most of the power would actually be carried in the vacuum, not in the copper itself. The copper actually gives rise to loss in the system. Yes, but you need the copper to establish the boundary conditions, which I'm going to talk about in a couple classes.
And you'd probably need enough copper so that it doesn't easily break?
No, you can coat it on plastic. No, you don't need that much copper. Yeah, but basically it comes to the point where there are other constraints on the system than how much copper you need to carry the current, because most of the power is not being carried in the conductor itself. It's being carried in the space around the conductor. And we'll deal with that in a couple of classes when we talk about waveguides. Adam?
How would this affect like a Faraday cage? Could you make a Faraday cage so thin that it wouldn't actually have the same properties?
Oh, certainly. At different wavelengths, it'll have different properties,
Okay.
yes.
So if there's a point where like certain radio wave could go through something.
Well, okay. Yes, certainly. Let's see. Yeah, so what you need to do is for the particular wavelengths that you're interested in, you work out what the skin depth at that wavelength is. We run into some problems with DC here, okay?
Okay.
But you work out what the skin depth at that wavelength is, and that's how much metal you need. I had an eraser. Okay. Let's see. I will, I just wanted to put this up to remind you what we were talking about now. I'm going to erase it and talk about one more thing to do with waves on metals. 2 more things. So basically, we have an imaginary dielectric function. The magnitude of the components in the imaginary dielectric function depend upon the conductivity of the material. And so we're going to need a model for the conductivity of the material, which I'll talk about in a couple of minutes. But first, now that we know the behavior of the waves in the metals and incident and what the boundary conditions have to be on the surfaces, we can once again work out the rules for an incident wave on a metal surface. And we have a complex index of refraction, which is what we did when we wrote down K before. We were really talking about index of refraction. All right. And what we know is that the transmitted wave so I've got prime is transmitted, double prime is reflected. The transmitted wave that we deduced before looks like this. Oops. This is the outer material. I'll make it real. Although, even if I had material out here which was had a complex index of refraction, it would just be that. The ratio of the 2 fields is the same thing that we had before when we worked it out for real indices of refraction, except now we've got complex numbers in here. Right? The one that interests me the most is this one, the reflection coefficient.
Those are normal incidents?
Oh, sorry, I should have said this. I actually intended to give it to you at angle, and I have, I believe, a computer program that does that correctly. But when I sat down and began to work it out in closed form, then it turns out to be fairly complicated, and there's not much point to just writing it down. And then I looked to see whether I could find a cleaner closed form in some of the textbooks. And in fact, the graduate textbook, Jackson, that is well known for just diving in and going into all the gory details, says at this point, I'll do it for normal incidents. It's too complicated to do for an arbitrary angle. So if you need it, if it turns out that you need it sometime in the next, for most of you, year and a quarter, just come see me. And perhaps by then, my research assistant will have gotten the program right.
That part is right. The part you
Okay.
didn't help me on.
But the bottom line is that for normal incidents, it's really simple. And basically, let's say, what do you take away from this? If we're reflecting off of a metal, let's say we've got a vacuum incident on metal, then I take that out, and I still have a complex index of refraction in here, which comes from this, right? How I take that square root depends upon what limit I'm in. Again, if it's a really good conductor, this is big and this is small, and as a result, then I get the 45-degree 1 plus I, right? If it's a poor conductor, then I Taylor expand this, and I just get an imaginary part, which is 2 pi sigma over omega times mu, right? So the way that you get the index of refraction, complex index of refraction, is pretty straightforward, unless we're right in that intermediate case, and then we actually have to take the square root carefully and properly for each case, right? But it's complex. And as a result, what that means is that the phase of the wave changes as it passes through, as it reflects off of the surface. And actually, we can use the way in which the phase changes as for different polarizations at different angles. Normal incidents, there's just one phase change, okay? But for incidents at an angle, we'll get one phase change for the S polarization and a different phase change for the P polarization. And by measuring the change in phase, for example, we put circularly polarized light incident on the surface, and we end up with elliptically polarized light after it reflects. By measuring the ellipse, we can determine what the change in phase was, and from that, we can determine what the optical constants of the material must have been, the real and imaginary parts separately. And that technique is called ellipsometry. You put a well-defined polarization onto the surface. In fact, there are some tricks with respect to how you choose the incident polarization. And then you measure the outgoing polarization, and from that you determine the optical constants of the material that you just reflected off of. Yeah, I'm going to leave it at that. There are, in the notes that I'm making available, I have the special cases for a poor conductor and a good conductor that would apply here, but I'm not going to write those down. I'll write one down. One special case is for a good conductor. I'm only writing it down because it's simple. All right. For a good conductor, the index of refraction becomes simple. It's 1 plus I, right? And the result is that the reflection coefficient, which is the the product of the complex Fresnel reflection coefficient, reflection field over incident field, times its complex conjugate, right, is just approximately 1 minus 2 skin depth over wavelength times the real index of refraction. The real part of the index of refraction. Okay? So the reflectivity depends upon the skin depth in the material, which is related to the conductivity. Where's the difference? You know, why is that happening? It's because the further you penetrate into the metal, and that means that it's not such a good conductor, the more Joule heating you're going to get of the metal. So all the loss in the reflection is actually due to absorption in the metal. And the deeper the field can go into the metal, the more absorption there is. Okay, so that does not finish electric fields and conductors. That finishes boundaries. And I have one more special case that I want to talk about, but I have to talk about models for conductivity first. Up to this point, I just said, we've got the conductivity that goes into the calculation of the propagation of the wave. You just take sigma and you stick it into the propagation of the wave. The special case that I want to talk about, we need to understand the source of the conductivity. Special case of a plasma. All right? And for a plasma, basically what we've got are relatively immobile ions. So I'm talking about a gaseous plasma. Right? Relatively far apart with electrons on average yielding something which is neutral over a volume of several hundred ions, let's say, that it will be neutral, right? But the electrons and the ions are separately mobile. However, the electrons are going to respond much more quickly to an electric field. They're going to accelerate 2,000 times faster than the ions. Right? So basically, when I have an electromagnetic wave incident upon a plasma, the electrons move around freely, they accelerate, and the ions just sort of sit there, maintaining neutrality for the whole thing. But that's about the only, they can serve two roles. One is that electrons can scatter off of them, and that will limit the conductivity of the plasma. However, if I apply a field in such a way, at a high enough frequency, that the electrons don't actually move all the way from one ion to the next, actually, it's even a greater distance than that. Basically, if they can move some distance without scattering off an ion, which is going to be a significantly greater distance than the distance between the ions, then I've basically just got a material in which the electrons move without scattering. There's no loss at all in the material. All right? And the overall model for a situation where I have electrons that can move freely in the presence of ions, even with scattering, is called the Drude model. And this was the first simple model for conductivity of metals, but it applies to plasmas better than it does to metals, actually. The history is just, I found it interesting because I somehow imagined that the Drude model was ancient, and it is, right? But it turns out that it's like 1905. So it was actually proposed in the same year. What? What?
That's pretty ancient.
Yes, but it's the same year that special relativity was proposed, and the photoelectric effect and Brownian motion was finally understood. So it actually is a modern physics concept. All right. But basically, then you just think about the motion of an electron that's moving freely in a field with some scattering, which would give rise to some damping. That is a very loud bird. Is it actually a bird or is it somebody's car?
We're filming.
All right. I'm scared to open the window.
Yo, Lord in here.
So you want to know what's going on in a system like this, you just treat the electrons classically.
Oh, wait.
I put a loss term in here for scattering in case I have scattering. And I have probably dropped a minus sign in here and I don't care. Got it? Yeah.
Brian will be sad to hear that.
Oh, you know what? I'll embed the minus sign in the E.
Okay, that works.
Okay? For rapidly oscillating fields, the electrons don't have a whole lot of opportunity to scatter, right? But actually, it's easy to understand what's going on here. We propose a field that looks like that, and then we ask about the response of the electrons to that, and you end up with a velocity response. So that's the current. Which is just that. And the current, I'm going to cheat here. The current density is equal to the charge density, which is the density of electrons times the electronic charge, right? Times the velocity. And current density has got to be equal to the conductivity times the applied field. And that was my applied field. I forgot the vector in there. Assume there's a vector in there. How about that? There we go. There's my applied field. So now that means that I know that my conductivity for this plasma is the charge density over m. Oh, sorry. This is the electron density. This is only the electrons that are moving. The net charge density is 0. So I'm just taking the charges that are moving to estimate the current. So I can write this like this. E squared times the electron density, because that was charge density there, over mass of the electron. My damping factor, I omega. So the conductivity is complex. All right. That applies, actually, that's the Drude model for metals. Okay? For a tenuous plasma, just because I wanted to use the word tenuous, just like your understanding, is, so for a tenuous plasma, the scattering is small. And then a really weird thing happens, or the consequence will be really weird and neat, which is that the conductivity then just becomes imaginary because the damping's small. So I just end up with E squared n over m e I omega. I want to rationalize it. And so I get an I up there. There's a phase change in there. I know when I brought the I up, I got a minus sign. I'm going to ignore it. And that's the conductivity. That's the conductivity of the plasma. It is complex. Actually, I'm not. No, that's right. I take it back. I had a minus sign here. And when I brought the I up, I lost the minus sign. Good. So that works. I didn't have to cheat on the sign. Right. So that means then then, since I know the conductivity, and I can then deduce the wave vector from that, the index of refraction, yeah, I'll just write down the index of refraction. The index of refraction is I'll write it this way. N squared is equal to 1 minus I've written a simple form here. 1 minus omega sub p squared over omega squared, because that's the form that it takes, where omega sub p is called the plasma frequency. And it's 4 pi n e squared over n. And above the plasma frequency, so if omega is greater than omega p, then the index of refraction is real. Below the plasma frequency, omega less than omega p, the index of refraction is purely imaginary. So it goes from real to imaginary. Below the plasma frequency, yes.
It's
Oh.
an unrelated, or semi-related question.
Go ahead.
How do we make the jump from the Drew model to what we know, which is that there are materials with anisotropic conductivities?
Oh, yeah. Yeah, this is such a, the Drude model is just ions with electrons model, all right? It's wrong,
Yes.
all right? It's an isotropic model for number one. In order to go to the next stage, okay, so there are a series. Number one, it's wrong because it ignores occupation function. That is, that all electrons below the Fermi level, all states below the Fermi level are going to be full and above the Fermi level are going to be empty. So it actually miscounts the number. It works fine for plasma, right? It actually works just great for plasma because let's say you've got a very small number of electrons in a large volume, which means that we actually don't have any the energies of the electrons are not influenced by quantum mechanics, right? So the Drude model is just fine for plasmas. And when we go to solids, we run into the problem the electron density becomes so high that that for a given volume, the electrons fully occupy a significant set of states, and we have to actually pay attention to the Fermi occupation function for electronic states. Plus let's see, there's the Pauli exclusion principle, Hund's rule, which is really the Fermi function, which basically, Hund's rule says start filling at the bottom and fill up, all right? Which is basically what the Fermi function says, fill at the bottom and fill up. So it turns out that in a real metal, let's say even in isotropic metal, the number of mobile electrons is much smaller than the total number of electrons in the system. You forget about valence electrons. We're talking about, or rather, electrons in the core orbitals. Those won't conduct anyway. But even for the electrons in the valence band, valence and conduction bands, only a small number of those are going to yield a net response to the application of a field. If you look carefully at, quantum mechanically at what happens when you apply an electric field to electrons that are in full orbitals, is that you'll cause one electron to accelerate this way and another electron to accelerate equally in the opposite direction when you apply a field. So low energy electrons. So I've got some band of states. This was not my intent to talk about, but it's fun anyway. It keeps me from having to talk about retarded potentials. And here is the density of states available as a function of energy. And so this is energy, and this might be the valence band of a material. Okay? And I've drawn this density of states because if you actually solve for what the shape of the density of states in a box is, it'll turn out that it looks like the energy to the 1/2 power at the edges. And then in the middle, it's got to do something else. We'll draw it like that. So at 0 Kelvin, we fill the system up, and we put the electrons into the system, and they occupy all of these states like so, right? I guess I need to say one more thing, right? Which is that a full band, so I take this band and I completely fill it with electrons, does not conduct. And that's because, it's not because the electrons don't respond to the electric field, it's because of this equality. That if I if I accelerate an electron this way, I must accelerate an electron in the opposite direction. And they always compensate, and you get no net current in, quantum mechanically in a system like this. Turns out that all the conduction ends up right at this surface here. So these guys don't actually conduct. These guys are the guys that conduct. At finite temperature, the occupation of this state looks something like that. So I get rid of all of this. I've got states there, but they're empty, all right? And all the conduction occurs in there. So the Drude model has to be corrected at the least for the number of electrons which are available to conduct. So that's number one. That correction for the number of electrons is called the Sommerfeld model. And then Sommerfeld also did his electromagnetics a lot more carefully than Drude did. But the Drude model explains the overall behavior pretty well and works fine for plasmas. Then we have the next complication here, which is that when I put those electrons in a crystalline solid, so then what I have to ask is, how does a given electron accelerate under the action of a field? And that will depend upon how the electron interacts with the atoms in the solid, right? And the way that we deduce how the electrons interact with the atoms in the solid is to solve the Schrödinger equation for a periodic potential. And you have to do it for a three-dimensional periodic potential, which ends up giving you, you can draw a kinetic energy as a function of crystal momentum graph. Right. Okay. Which tells you how the electrons accelerate. If an electron, so we would make a plot that looks like this to describe what's going on. I've just drawn energy, number of states that are available. Right? In order to really understand what's going on, you're going to plot energy as a function of, I'll just write here, I'm cheating you a little bit, momentum. Right? And for a completely free electron, something that's not in a crystal at all, that just looks like that, p squared over 2m. All right? I put that in a crystal, this gets distorted. And it ends up perhaps looking maybe something more like this, where this point here corresponds to the interference condition where waves that are trying to propagate forward reflect backwards with a, they reflect backwards strongly, so it turns out it's not possible to propagate the electron through the solid. So you end up with an E versus, it's really K, but E versus K relationship looks like that. You look at the curvature here, and you deduce the amount of acceleration for a given applied electric field from the momentum versus energy curve, right? That relationship is called the effective mass of the electrons. For electrons in solids, the effective mass depends upon which way they are traveling. So that was much more than you asked for, I suspect, but maybe much less than you asked for.
Much less. Sorry.
Okay, I can give you more at another time.
The course next year, The course next semester?
Yeah, someone will be teaching, well, there are two courses next year. One is solid state physics, which, turn that off, please.